Hey everyone, welcome to the second video for section 2.4. In this video, we're going to go back to the theorems we talked about in the last video and sort of do more of a comparison between them and talk about the main differences we get between linear and nonlinear equations because the theorems are a little bit different and it's fairly significant in the ways they're different. So we'll talk about that and move forward doing some examples about how you can actually use these to do some stuff. All right, let's jump on into it. So I have pulled up my slide from last time that I wrote the two theorems on, and I did it well enough that I got them to go on the same screen, so we just talk about this all at once. And I underlined things in different colors while we were talking about the theorems last time. And now I'll talk about what I did there. And it turns out I didn't actually match them up directly. So we'll fix some of that, and we'll do that. So the things that are the same, right? Things that are the same, some sort of continuity assumption. We're assuming that P and G are continuous. We're assuming that F and df dy are continuous. And that's one assumption that's the same. And the result's also the same, right? You get the result of exists a unique solution. Exists a unique solution. Right, so the ideas of the theorems are the same. You make some assumption about continuity of some parts of the ODE you're trying to solve. And at the end of it, you get a solution out of it, and you get a unique solution out of it. So the ideas are the same, but the result you get is a little bit different, and that's the part I underlined in green. So for the linear equation, we get that once we have P and G continuous on an interval a to b, I automatically get a unique solution for all t in a to b. Everywhere across the interval, I get it immediately. It doesn't matter. That's the only something I need to make. I get the solution everywhere immediately. So if P and G have discontinuities at 0 and 4, I know the only place I can have problems are at 0 and 4, and I will always get solutions up to 0 or up to 4, depending on my situation. On the other hand, for the nonlinear equations, I get a solution in some interval t0 minus h t plus h. So I don't necessarily get all of alpha to beta. I just get some little subset. And the reason there is that I have a rectangle where I know things are continuous and nice. However, this rectangle and this thing being nice depends on y, which is my solution. So while I may have my functions f and df dy continuous all the way from t equals alpha to t equals beta in a rectangle, it's possible that somewhere in the middle of that rectangle, my solution, my y, shoots up above delta and breaks out of the rectangle and then breaks continuity. So even though t isn't getting too far away to break continuity, y might be. So let me draw a quick sketch of that so we can see what that looks like and what I'm sort of talking about. So say we know, so I have my axes here, and we know this is t and this is y, and we know f and df dy are continuous here in that rectangle. And I want to start at this point right here. So I want to start. Now, for a linear equation, we would know that I can always go all the way out to here. So this would be, say, our beta. This is our alpha. So for linear equations, I would know that I can go all the way to the left to alpha and all the way to the right to beta without a problem. However, the issue is for nonlinear, my curve might do something like this. This might be my solution curve. Once I break this rectangle here, I have no idea if I'm continuous anymore. I haven't gone further to the right of beta, but I've lost where I might be continuous. So in that case, I could lose my solution at that point here. Might be the time where my solution stops existing. And I have no way of knowing that a priori before I solve the actual problem. Right? I have no way of knowing when my solution is going to hit that point unless I actually solve the equation. So this idea of where my curve might leave my rectangle, so this point to this point, this is the idea of the interval of definition for an equation. It's where the solution exists in that sense. Another way this can break down is if our curve goes vertical. So let me draw another example with a blue curve here. So say I start at this point here, and my curve pulls one of these numbers right on that line. Now what happens here, as I cross this line, I lose my solution. Why do I lose it? Because at that point, y is no longer a function of t, right? We assumed that y was a function of t, which means I can't have curves that go vertical and double back on themselves. So those are two ways that I can lose solutions, and both of them give rise to intervals of definition. All right, so let's look at a couple examples of this and what we can do here. So example one is going to be a linear equation. And I want to deal with three different initial conditions. y1 of 1 equals 2, y2 of negative 1 equals 3, and y3 of 5 equals 1. Now this is a linear equation, which means once we write it in standard form, so standard form means I need the coefficient of y prime to be 0. So I get y prime plus 3 over ty plus equals 4 over t minus 3 is my standard form. And I know by the linear existence uniqueness theorem that I will have a solution so long as both p of t, which is this guy, and g of t, which is this guy, are continuous. So where are my only problems here? I only have problems at t equals 0 and t equals 3. That's where these things become discontinuous. So what does that mean for my solutions? Well, that means y1 exists on the interval between 0 and 3. Because it starts at 1, it can go as far left as 0, and because it's linear, we know it goes all the way to 0. And as far right as 3, but again, linear, we know it goes all the way to 3. y2 exists on minus infinity up to 0. We start at minus 1. If we're going left from minus 1, we can go as far as we want. There's no discontinuity points that way, so we can keep all the way to minus infinity and up to 0. And similarly, y3 exists on 3 to infinity by the same logic as before. So for linear equations, all you have to do is look for where your functions are not continuous, and you get everything up to those points every time, no matter what. That's just how the equations work. Now for example 2, we're going to look at a nonlinear equation. So this ODE we're trying to solve. Where does this guy have problems? Well, this only has problems where x is 1 or y is 1. So basically it's continuous everywhere except along these two red lines. X equals 1 and y equals 1. So we know that if we start in one of those four quadrants in terms of the red axes, we have to stay there because we can't cross over the bad spots. But the issue is no matter where I start in X, say I start here, until I solve the problem, I have no idea if or how quickly I'm going to hit this line. I could just go like this and not hit it ever, or there's a possibility that I could just start here and dive down and hit the line right away. Hit the line right away, that means my solution stops there, and that's where things go south. So I don't really know until I solve the problem how long my solution is going to last. I know it can't cross x equals 1. That I know for a fact. How long it can last beyond that, I don't know because I don't know when I'm going to end up crossing y equals 1 until I actually solve the problem. So two other examples to look at that I'm not really going to talk about are examples 3 and 4 in the book. I want to definitely look those two over. They're definitely nice to read and see what's going on with them. We'll probably end up talking a little bit about both of them in class. They may be on some of your problems to work on tomorrow in class. But they're definitely good to look over, take a look at it and see what it means. Basically what they're saying is that if you don't meet the conditions of the theorem, you don't get uniqueness. And then we have example 4, which talks about blow up and stuff, which is going to be one of your Maple Labs, I think, too. All right, I think that's all I really want to hit for this video. In the next one, we'll talk about other differences between linear and nonlinear equations besides just the theorems. This is something definitely to think about. Make sure you understand sort of how these things come together and how you can use them to sort of analyze problems before you actually solve them. All right, thanks a lot for watching, and I'll see you in the next video.